let us explore a fascinating puzzle at the intersection of quantum gravity and the nature of space-time, the Quantum Causal Set Paradox. Some physicists suspect that at the smallest possible scale, the Planck scale, about 10 to the power minus 35 meters, space-time is not smooth and continuous, but instead discrete, like the pixels of a digital screen. This idea is known as the causal set hypothesis, but it raises a profound question. If space-time is made of discrete atoms, of space and time, how do causal relations, the fabric of cause and effect, survive this discretization? In general relativity, space-time is continuous and smooth. Events are connected by light cones, which tell us which events can influence each other and in what order. This structure defines causality. If event A is inside the past light cone of event B, then A can cause B. But if space-time is made of discrete points, like a network of nodes, there are no smooth light cones. You might ask, how can we preserve the concept of cause and effect in such a world? The causal set approach tries to solve this by making causal relationships themselves fundamental. Instead of starting with space-time and then asking which events influence which, the theory starts with a set of events and the causal links between them. In other words, space-time geometry is built up from the order of these relationships, much like how a movie is built from individual frames. But this leads to the paradox. If space-time is discrete, how do we recover the smooth causal structure we observe at larger scales? For example, what determines the precise angle of a light cone in a discrete network? And how can quantum uncertainty fit together with the sharpness of causal links? At small scales, there is a risk that events could lose their clear ordering, potentially leading to paradoxical situations where the distinction between cause and effect breaks down. This question is not just theoretical. If causal order is fundamental, it could explain why time appears to flow in one direction, and why quantum entanglement and relativity seem to be consistent despite their different views of information transfer. But if causal order becomes fuzzy at the Planck scale, it might lead to violations of the familiar second law of thermodynamics, or even allow for causal loops, where effects influence their own causes. Why does this matter? Because understanding the quantum structure of spacetime could be the key to unifying quantum mechanics and general relativity. Experiments using gravitational waves, high-energy particle collisions, or quantum entanglement might eventually detect signatures of discreteness, tiny deviations from the predictions of continuous spacetime. The quantum causal set paradox pushes us to rethink not just what spacetime is made of, but also what it means for one event to cause another. Could causality itself be the deepest layer of reality, more fundamental than space and time? Or will a future theory show that even causality emerges from something deeper? Quantum gravity theories suggest that space-time may not be continuous, but composed of discrete units at the Planck scale, 10 to the power minus 35 meters. Continuity leads to mathematical infinities in general relativity and quantum field theory, motivating the idea of a fundamental space-time lattice. Discreteness could resolve singularities inside black holes and at the Big Bang. The causal set theory proposes that space-time is a collection of discrete events linked by cause and effect relations. However, this raises a paradox. How can smooth causal structures persist in a granular space-time? General relativity assumes smooth curves for light cones, but discretization could break these paths. It is like replacing a continuous line drawing with a dotted one and wondering how the picture remains coherent. In relativity, causal structure is determined by light cones. If an event lies within another's light cone, it can be influenced by it. This structure is continuous, with infinitely many intermediate points between cause and effect. Removing continuity threatens the very notion of causality, because there may be gaps between discrete spacetime elements. Without causality, physics loses its predictive power. Preserving causal order is therefore essential in any quantum gravity framework. In relativity, signals cannot travel faster than light, preserving causal order everywhere. It is like a domino chain. Remove too many dominoes, and the chain reaction stops. The causal set approach posits that spacetime consists of discrete events partially ordered by causality. Each element represents a point-like atom of spacetime, and the ordering encodes which events can influence which. The large-scale continuum of spacetime emerges statistically from this discrete set. If the number of elements per unit volume is extremely high, the spacetime graininess might be imperceptible at observable scales. But whether causal relations remain consistent in this picture is still debated. Discrete causal sets can statistically reproduce Minkowski's spacetime in simulations, but with subtle fluctuations. It is like a pixelated photograph that appears smooth when viewed from far away. Discretizing spacetime introduces potential problems with causal links jumping or being lost between points. At small scales, fluctuations could disrupt light cones, leading to violations of relativistic causality. If discrete elements are randomly distributed, how can we ensure macroscopic causal order? Too much irregularity could allow closed time-like curves or superluminal signaling, breaking the foundations of physics. This is the core of the Quantum Causal Set Paradox. In a coarse lattice, signals might skip nodes, violating locality and causality. It is like a train track missing rails. The train might derail or take unintended shortcuts. Causal set theory tries to avoid paradoxes by making causality fundamental rather than emergent. The ordering of elements defines spacetime's structure, rather than the other way around. This ensures that events always follow a consistent causal sequence, even in a discrete framework. Large-scale smoothness arises statistically as the number of events becomes enormous. This flips the usual logic. Instead of spacetime giving rise to causality, causality builds spacetime. Each new atom of spacetime is linked only to its predecessors, preserving temporal order. It is like constructing a building brick by brick, ensuring each layer supports the next. One challenge is maintaining Lorentz invariance, the idea that the laws of physics are the same for all observers in a discrete model. A fixed lattice would pick out preferred directions, breaking relativity's symmetry. Causal set theory addresses this by using random distributions of events, avoiding directional bias. But randomness can introduce statistical noise that disrupts causal order. Balancing symmetry and stability is a key open problem. Poisson sprinkling is used to generate discrete points uniformly, without privileging any reference frame. It is like randomly scattering seeds in a field so the pattern looks uniform from any angle. Quantum theory adds further complexity. Causal links might themselves fluctuate. Superpositions of different causal orders could occur, as suggested by quantum information experiments. How do we reconcile definite causal order at macroscopic scales with possible causal indeterminacy at the Planck scale? This tension lies at the heart of merging quantum mechanics and relativity. New mathematical tools are needed to model such quantum causal structures. Quantum switches in lab experiments allow operations to occur in indefinite causal order. It is like two chefs cooking a dish where neither is definitively first or second, yet the meal still turns out. Testing discreteness at the Planck scale is incredibly difficult, but subtle effects might be detectable. Experiments with high-energy cosmic rays, gravitational waves, or black hole evaporation could reveal spacetime graininess. Quantum entanglement tests might also probe causal fluctuations. These observations would help determine if spacetime is continuous or discrete. Until then, the paradox remains a largely theoretical challenge. Some models predict minute time delays in gamma-ray bursts traveling across the universe if spacetime is discrete. It is like listening for faint static on a radio to detect imperfections in the signal path. The quantum causal set paradox forces us to question whether continuity is a fundamental feature of reality. If space-time is emergent from discrete causal relations, our everyday notions of distance and time may be approximate. Solving this paradox would unify relativity and quantum theory at their deepest level. It could also clarify whether the universe's history is fundamentally deterministic or probabilistic. Either outcome would transform physics and philosophy. Resolving the paradox might explain how black holes process and release information. It is like discovering whether the fabric of the universe is woven from continuous threads or tiny individual beads.